Okay, section 3.2, video part 2. Continuing where we left off here. I've got some problems here for you to attempt to solve. I encourage you to pause the video, try these, and resume the video. So how this first one works out, using the properties on the previous slide that we had just finished looking at, these properties here, which you will find on page 189. You might want to go there and look. So the first one, log base 5 of something equals log base 5 of something. Well, the only way that's possible is if those two somethings are in fact equal. So 3x minus 1 will equal 11. So we'll solve that. 3x equals 12. Therefore, x will equal 4. This one here, number 14, we have 6 to the power of x equals 36. 6 to the power of x is 36. So we'll recognize that as 6 squared, so x will equal 2. In our next one here, we have 7 to some power is going to equal 7 to the x. So 7 to what power will equal 7 to the x? That would be x. 7 to the x power will equal 7 to the x power. Here we have one using the last property. 8 to the power of log base 8 of 9. So first thing we should probably do is take a look at what log base 8 of 9 means. Log base 8 of 9 is going to equal some number. And whatever it equals, 8 to that power is going to give you 9. Well, imagine this says y. 8 to that power will equal what? It's going to equal 9. So you should review those, try and make yourself as familiar with those and as comfortable with those as possible. Here's an example of graphing. So when we're graphing logarithmic functions, we want to remember that, first of all, I told you earlier that a logarithm is an inverse of an exponential graph. So with that knowledge, when graphing logarithmic functions, remember that a function and its inverse have graphs that are symmetric across the line y equals x. The line y equals x, if you've forgotten, is right here. So if I graph y equals x, this is going to be a part of this. Here's the line y equals x. So y equals 2 to the x, we know what that graph looks like. We've already done this in the last chapter, or last section rather. So if we graph y equals 2 to the x, we'll do that in blue. We'll choose some values and we'll evaluate the function. Okay, so 2 to the 0 power, 2 to the first power, 2 to the second power, 2 to the third power. So if we plot these points, we have 0, 1, 1, 2, right there, 2, 4, and 3, 8. Now what about the negatives? 2 to the negative 1, that's 1 over 2 to the positive 1, or 1/2. 2 to the negative 2 is 1 over a fourth. 2 to the negative 3 would be negative 3 would be 1 over 8, and so on. So we've seen this, and we know that there is an asymptote over here. So the graph never touches the x-axis. My graph isn't drawn perfect here, but you get the idea. So I would expect that the inverse of that, the logarithm graph, is going to be somewhere over here. So I'm using y equals 2 to the x to graph its inverse, which is the log base 2 of x. And I'll go into detail about why those are inverses of each other in a moment. But once we accept that they are inverses, to plot an inverse, I can just switch the coordinates. So if I'll do this in green here. So instead of plotting the point 0, 1, I'm going to plot the point 1, 0. Instead of plotting 1, 2, I'm going to plot 2, comma 1. And I'm just going to flip all of these points. So I'm going to graph 4, comma 2 instead of 2, comma 4. I'm going to graph 8, comma 3 instead of 3, comma 8. And I'm going to graph 1/2 negative 1 instead of 1. I'm sorry, instead of negative 1/2, and so on. So the asymptote here is going to become the y-axis for this one. So this graph will come from down here. This is an asymptote. It's not touching that line, and it curves up like this. So this one here is log base 2 of x, the green graph, and the blue graph is 2 to the x power. So we graph y equals 2 to the x power in order to help us graph y equals log base 2 of x. I don't remember. Okay, so let me intervene here. There's a slide I just realized I want to add here. I want to go into detail about why we know that these two functions, y equals 2 to the x and the log base 2 of x, how do we know they're inverses? So let's go do that now. Let's call this g of x, actually. Well, one way that we can show this, if you remember, one way to show that two functions are inverses, this is actually a test question a couple of last chapter. If I can show that f of g of x equals x and g of f of x equals x, then I will have demonstrated that f of x and g of x are inverses. So I'm going to do exactly that. So the first thing I'm going to do is let's evaluate f of g of x. Well, that means I'm going to take log base 2 of x and I'm going to put it up here. So I'm going to take 2 to the power of log base 2 of x. What does this equal? Well, just like we said before, let's take a look at this exponent up here, log base 2 of x. What does that mean? Log base 2 of x, let's say it's going to equal something called y. This means 2 to the y power will give me x. So if I replace this with y, I'm doing 2 to the y power. What am I going to get? I'm going to get x. So that one works. I meant to put that in black. Now the other one, I want to show that g of f of x also equals x. So that means I'm going to take log base 2 of, instead of putting x there, I'm going to put 2 to the x there. Well, of course this equals x because 2 to the x power equals 2 to the x power. So this proves to us that 2 to the x power and log base 2 of x are in fact inverses, and it reinforces what we did here. Now, we can't verify this in our calculator yet because our calculator, we're only capable of typing in log base 10 with the LOG button, or we have another log called a natural log. And we'll try that in a moment. So right now I want to try another graph here. This time I'm going to have you try this without using the inverse function. So here we're just going to try to fill out a table. So we'll pick some x values. We'll evaluate them and we'll see what we get. So this is kind of backwards thinking here. If we think about how we're going to evaluate this, we know what the function is. In fact, maybe it's easier for you if I write this out as log base 10 of x equals f of x. That's the way I've been writing it so far, and so I'll put it that way now. So to do this, I'm going to use as familiar of numbers as possible. First number I'm going to put up here, even though I'm not going to be able to graph this point on my graph, because I don't have enough room, but is the x value of 100. If I put 100 in here, I'm going to ask myself, log base 10 of 100 equals what? Well, that means 10 to this power equals 100. That would equal a 2. So another familiar number we could use would be, say, 10. Well, this is like saying log base 10 of 10 equals what? Well, 10 to what power would give me 10? 10 to the first power. Let's use the number 1. So we're going to ask ourselves, log base 10 of 1 equals what? 10 to what power equals 1? 10 to the 0 power. So like I said, it's kind of backwards thinking here. Let's look at, let's see, we did 10. How about 1/10? So for this one, we're going to ask ourselves, log base 10 of 1/10 equals what? Well, 10 to what power equals 1/10? 10 to the negative 1 power. So what would 10 to the negative 2 power give me? It would give me 1/100. So this is enough to at least plot and take a look at the shape of the graph. I'm going to plot the point 10, 1 right there. I'm going to plot the point 1, 0, which is going to be right there. We're going to plot the point 1/10, negative 1. Well, that's going to basically be right here. Then 1/100th, negative 2. And you can see that this is just going to keep on getting closer and closer and closer here. So this graph is going to do something like this. And we can plug in more values because this is log 10. I could ask myself, like, what is it going to equal when x is, say, 4? So if you want to go to your calculator for that, type in the log of 4. Let's quit that. You see that it's 0.6, so up here. So I'm not too far off. The graph isn't perfect. But this is the graph. That is what a logarithmic graph looks like, and we would determine it just by doing this, making a table. Now we could also type in, since it's log base 10, I could just type in log of x, and we could view this in the same window, the standard viewing window, and we see basically this graph. If you want to look a little bit closer at it, since the graph doesn't take up that much space, we could just limit this window to the maximum of 2, and we'll see it a little bit better there. So that's our graph. Now the natural logarithmic function, this is when we have, and I know it's hard to see what I wrote there, this is when we have log base e, the irrational number e. This is called a natural logarithmic function, and we write this one as ln, log or natural log. That's how they write that. This is a button on your calculator. So this in the common log base 10 are very common. So natural log button, you'll see it right here. So if I wanted to know what is the natural log of a number like e to what power will equal that number? It should be 1, because e to the first power equals e to the first power. So these work the same way as the common logs do. We've got a series of properties here. These are the same properties as you'll see with the common logarithm. So nothing different there. These you'll see in the book as well. Now the last thing I'm going to do here is this page, but I'm going to stop this video and we'll have to finish that in a third video.